Hello, everyone, and welcome to this presentation on standardizing computational storage at the 2023 Compute, Memory, and Storage Summit. My name is Jason Molgard, and I'm here with Bill Martin, and we are co-chairs of the SNIA Computational Storage Technical Working Group. So today in our presentation on the agenda, we'll start with a little bit of a status on where we are with the SNIA Computational Storage standard, and then jump into an overview of the computational storage architecture, as well as an overview of the computational storage API that we're developing. We'll compare SNIA and NVMe computational storage, and then talk about next steps and wrap up. So we're still getting a lot of participation, a lot of interest in computational storage in the SNIA computational storage TWG. We've got 48 companies, 258 individual members. You can see the list of all of the companies that have joined the TWG on the right-hand side. We've got a lot of internal and external activities that are in progress. We're working with the Computational Storage Special Interest Group on webinars, blogs, and events, the SDXI, the Smart Data Accelerator Interface, which is a different TWG in SNIA, on some group collaboration for the two technologies. And we'll get into that a little bit more later in the presentation. We're working with the security TWG on security, as we are firmly believed that without proper security, then computational storage may not be successful. And of course, we don't want that. And then externally, we're collaborating with NVM Express, ensuring that the work that we're doing aligns with everything that they have going on, and the two technologies will play together. So we're working on two main documents. The architectural document, version 1.0, is available. It's been released last summer. You can go download a copy from the SNIA website. We're working on a 1.1 enhancement to that, which includes security enhancements for multiple tenants, chaining of commands, and expansion of use cases. API, we have a 0.8 that is available for public review that you can also go download from the SNIA website. This version is incomplete at this point, but it shows the current state of where we're at. We welcome your feedback on that 0.8. And of course, we're going to press forward and get to that 1.0 on the API, adding in things like abort and reset handling, device memory management, and support for the NVMe computational programs, along with other miscellaneous updates to get to a complete 1.0. So let's go ahead and launch into the architecture overview. So in the architecture, we've defined 3 different architecture types for computational storage. So the first one is over here on the left-hand side. We've got a computational storage processor, or a CSP. And this is essentially a device that does not have any persistent memory. It attaches to the fabric of your system and can offload the host, performing computations on your storage, on your stored data, but it doesn't actually store any data itself. In the middle here, we have the computational storage drive, or CSD. This is a well-known storage drive, an SSD, for example, with additional compute capabilities built in. And then over on the right-hand side, we have the computational storage array. This is an array that you may be familiar with that happens to have some compute capabilities at the array level, but it may also have a computational storage drive as part of its array of disks. And so this actually could provide multiple levels of offload, where you could do computation at the array level or at the drive level. Now, one thing I think you'll notice from all of these diagrams is that they all contain this teal-colored block labeled computational storage resources. And so we will get into that here in the next slide. All right, so let's take a look at some of these resources and what all of these things are. So starting with our first one here, we've got the computational storage resources in general. And these are the resources that are just available and necessary for a device to store and execute a function. So what is a computational storage function? All right, a computational storage function, or CSF, this is a specific function that can be configured and executed by a computational storage engine in a computational storage engine environment. So this is the compute function. This is what you want to do and have it operate on your data. All right, so then what's a computational storage engine? So a computational storage engine, or CSE, this is the resource that can be programmed to provide a specific operation. So a couple of examples, you could think of a general purpose CPU, that's a computational storage engine. You could think of an FPGA, that would also be a computational storage engine. All right, so computational storage engine environment that I mentioned previously, what is that? So this is an operating environment for the computational storage engine. So if you're thinking general purpose CPU, then you could think of the operating system as the computational storage engine environment. If you're thinking FPGA for your computational storage engine, then the computational storage engine environment would be the bit file that configures that FPGA to take on an identity and become a function. So no matter what your function is, likely you're going to need some type of memory for it to operate on, some scratch pad or otherwise. And so we've created function data memory, or FDM. And this is the memory that's available for those computational storage functions to use as they're operating. And the general pool of computational storage function, or of functional data memory of FDM, can be partitioned into subsections and then allocated as appropriate to a specific function. And so we've got the notion of allocated function data memory, or AFDM. So if we look at the teal box, I've covered all of the main blocks except for the resource repository. And I'll just mention that the resource repository is additional resources that may be present in a computational storage device, but are not activated. So they're not available to operate at that moment, but if they were activated, then they could become available. All right, well, let me go ahead and turn it over to Bill, who will walk us through security considerations.
So as Jason mentioned earlier, we worked with the security technical work group within SNIA to generate some security considerations for version 1.0 of the architecture. There were some assumptions that we made in preparing for those considerations. The assumptions are for version 1.0 that the environment consists of a single physical host or a virtual host with one or more CSXs. So this limits our security to the fact that you have a single host or virtual host that controls the security. The host is responsible for the security of the ecosystem that the CSXs operate within. The security requirements are comparable to the security requirements that are common to SSDs and HDDs. So we're not looking at extending the security requirements because of the computation. However, there are things that require privileged access, and the security considerations talk about the privileged access and which functions require that. Privileged access is elevated privileges necessary for operation. This would be like the system administrator has privileged accesses. We also talked about sanitization in the security considerations. When you sanitize, all instances of CSF operations should be terminated. All activated CSEs and CSFs should be deactivated. And all memory allocations associated with FDM should be removed and the associated FDM cleared. So these are basic recommendations, and security in version 1.0 is written as a set of recommendations for here are things that you should consider as you develop a computational storage device. Also in 1.0 is a section that talks about data at rest encryption. One of the key facts about data at rest encryption is that if your data at rest is encrypted and you want to perform a function on that data, then you may need to encrypt or decrypt the data in order to operate on it. So you would decrypt the data, perform your operation, and then re-encrypt your output such that your data is always encrypted. So that is another consideration that you need to consider when you're developing a computational storage device. Another is key management. The CSX may need to manage keys to support encryption or decryption of data. And there's a section that talks about all of the considerations that are necessary for doing that key management. Software security, because you are now executing functions, those functions in essence are software, that software may require verification of the integrity of the downloaded program. So you want to make certain that when you download it, something didn't accidentally happen, but also verification that the code originates from a particular source and has not been compromised. So you want to make certain that you don't have a rogue operator putting software onto your device and that you then execute and cause a security leak. Next, I'd like to talk about what we're looking at for version 1.1 in terms of security. We're extending security in 1.1 to considerations necessary for a multi-tenant environment. So the one thing in the last section that we talked about was all of those considerations were strictly about a single host or a single VM, in essence, a single tenant. So once you have multi-tenant, you need to develop trust relationships. There are a number of elements required for a trust relationship. The first of those is identification. So identification is exchange between participating parties, where a party says, this is who I am. The host says to the computational storage device, this is who I am. The computational storage device says back to the host, this is who I am. So there's an identification that goes between the two. But in addition to identification, you need authentication. It's done following identification, but it's an exchange of authentication information, and it's done with the same element as identification is done with. So if you did your identification between a VM and a computational storage engine environment, then your authentication is done at that level also. Once you've done authentication, then you have authorization. Authorization specifies what actions or specific resources a given party has access to or permission to do. It may be done at a lower level element than the element that was authenticated. So if I have authenticated at the computational storage device level, I may do authorization within that device at the computational storage engine environment level. And finally, there's access control. This controls access to elements of the CSX that are within the scope of the authorization. So notice that this is scoped at the authorization level. So if you've authorized at the computational storage engine environment level, then you can't in turn have access control of the computational storage element or the computational storage device that is above that level. This may be access to a CSE, a CSEE, or a CSF. So there are different elements of the trust relationship, and the identification, authentication, authorization, and access control may be done at different levels. So identification and authorization could be done at the CSX level. Authorization may be done at the CSEE level within the CSX, and access control may be at the CSF activated in the CSEE. So moving on, I'd like to just briefly cover an API overview. We're not going to go in depth here because there is another presentation coming up, and we'll talk about that after I go over a brief summary. But the SNIA Computational Storage API, as Jason said, it's currently at version 0.8 with a public review release, and we're working towards 1.0. So what does this do? This creates an interface from the application to the host software stack, which then communicates with the computational storage device. The goal here is that we have one set of APIs for all CSX types. So whether it's a processor, a drive, or an array, it has the same API. It has the same interface to the application. So the APIs hide device details. They hide the details about hardware. They hide the details about connectivity, whether you're local or remote, so that the application does not need to worry about what the device is that is out there. It simply sends its commands to the host software, which then goes into an API library and converts it into the appropriate commands for the device that you're talking with. So it abstracts device details like discovery. So discovery is not in terms of whatever the low-level discovery protocol is. It's at an API level that's consistent across everything. The same thing for access, the same thing for device memory, and whether device memory is mapped into host memory or not mapped into host memory. For near storage access, that's access to storage that is closely associated with the computational storage devices. Copying from or to device memory, downloading CSFs, executing the CSFs, and overall device management. So all of those things get abstracted by the API. It is an extensible interface where you have plugins that connect the CSX to abstracted APIs. So when your CSX is a particular device, the specifics of that are hidden or abstracted by the plugins. So that hides vendor-specific implementation details. Finally, the APIs are OS agnostic, so they are independent of the operating system. For more information about the SNIA CS API, please make certain that you attend or watch the SNIA Computational Storage API by Oscar Pinto that is part of the SNIA Compute, Memory, and Storage Summit. Next, I'd like to briefly talk about how SNIA and NVMe computational storage work together. As Jason mentioned early on, we do have an alliance agreement with NVMe, and we work to try to make certain that the two of these work together. So I will do a very high-level overview of what is in the NVMe architecture. So the NVMe architecture is made up of namespaces. In the NVMe architecture, there are two new namespaces being defined. One is the compute namespace. That's where you have your compute engines and you have your programs. The other is the subsystem local memory, and that is where all of the memory is that your programs operate on. So that memory is allocated as memory range sets to isolate one program from another. And that memory includes your program input, your program output, as well as any scratch pad that the program may require. And finally, you have NVMe namespaces. This is your persistent storage of data. This is what NVMe has had all along. These consist of NVM namespaces, which are logical block address spaces, your ZNS namespaces, which are zoned storage namespaces, and key value namespaces. So data is transferred between NVM namespaces and subsystem local memory using a copy command. So how do these things correlate? So in SNIA, we have the computational storage engine. In NVMe, we have a compute engine, which is actually a compute namespace. SNIA has a computational storage engine environment that is virtual in NVMe. We currently don't define an environment. We have a resource repository in SNIA where you have downloaded CSFs and CSEEs, preloaded CSFs and CSEEs. In NVMe, we have downloaded programs and we have device-defined programs. Activation, we use the same term in both. Function data memory in SNIA is equivalent to the subsystem local memory in NVMe. Allocated FDM in SNIA is equivalent to the memory range set, and device storage in SNIA is equivalent to the NVM namespaces. So we've looked at what are the same. Let's look at what the differences are. So SNIA defines a CSEE. So that's the execution environment, as Jason talked about. In NVMe, the CSEE is logical. There's no specific definition that is similar to the SNIA definition there. In SNIA, a CSF can directly access allocated function data memory or storage. In NVMe, programs only access memory range sets. NVMe does not allow a program to access directly the non-volatile storage. SNIA supports an indirect model where you have a model that writing to a certain area of memory or something triggers compute to be done on that transfer. NVMe only specifies an execute command. So to do any compute, you have to generate an execute command. With that, I'd like to turn it back over to Jason to talk about the next steps and where we're going.
Yeah, thank you, Bill. So we definitely want to kind of focus on where are we going forward from here. Certainly the big thing on our plate is completing that API 1.0 specification. We want to get all the details written into that specification and then release it publicly. Beyond that, we've already mentioned as well that we have the architecture and programming model 1.1 that we're working on, including the multi-tenant security considerations that Bill described, chaining of commands, and then some increase in the number of examples that we plan to include in that in order to try to make it provide new capabilities and new understanding for readers of that architecture and programming model. And then a big one that we're kind of focusing on as well is the collaboration between computational storage and SDXI. While these are on the surface orthogonal technologies, there's actually a lot of potential synergy between them, and so we're exploring how can these work together. So if we take a look at the next slide, here's a diagram of something that we have put together that we've developed in collaboration with the SDXI TWG. The red arrows are showing data movement between different memories from where the computational storage engine would potentially specify that movement. And the green arrow is data movement where the host is specifying the data movement. And for those of you who aren't familiar with SDXI, you can think of it just briefly as a DMA engine, a standardized DMA engine, where it can you can specify that you want to move data from one location to another, as with any other DMA, except that it is standardized. And it has some capabilities built in as well for data transformations, which could play a part in some of the compute in a computational storage device. So in this diagram, we're showing movement of data between two different computational storage devices, between the host memory and the device memory. Obviously, SDXI already supports natively data movement within memory of the host, but it could also potentially move data within the AFDM. So maybe you've got one block of AFDM and you want to move the data to a different block of AFDM so that a different function could operate on it. For example, SDXI may be able to do that data movement in a standard way. All right, so with that, let's kind of conclude. If that's interesting, whether it's any of the work we're doing on the API or the architecture and programming model or the work with SDXI, then please consider joining us. We're always looking for new folks to participate. Here's a couple of links. One to join SNIA if you're not already, and then another link to join the computational storage technical work group in order to participate in some of these activities. And so there's a couple of additional presentations as well on computational storage if you're interested in learning more. Obviously, Bill already mentioned one of them on the computational storage API by Oscar Pinto. So that one is definitely available, and we encourage you to take a look at that one. But if you want to know more about what's happening over in NVMe, then there's an NVMe computational storage presentation by Kim Malone and Bill Martin, and that will definitely get into more detail on how exactly the NVMe side of things is going to work and play together. So with that, we'd like to thank you for joining us for this presentation. On behalf of Bill Martin, I'm Jason Mulgard. We appreciate you taking your time. And we would also appreciate if you take a moment to rate this session. Thank you.